Good evening, everyone. Welcome to the problem solving sessions for week 11. I am Shreya, one of the TAs for this course, and today I'll be discussing concepts discussed during week 11 lectures, and hopefully, this will help you tackle the assignment questions as well. So, let's get started. So, in week 10, we learned about simple linear regression, which was essentially one response, that is y we had as our response or the dependent variable, and x was the independent variable or the predictor. Okay, and we had only one x variable. All right, and in such a setup we learned about methods of estimation of regression coefficients. The first one was the ordinary least squares or the OLS, and the second one that we learned was maximum likelihood. Okay, and then after learning this, we learned about some of the properties of the estimator, like whether it would be unbiased or not, and why would we want a minimum variance among the unbiased estimators, these sort of things. And then we proceeded to testing of hypothesis, where we learned how to test for individual regression coefficients. Okay, and once we learned that, we learned about how to get the confidence intervals and so on and so forth. Okay, so this is the all of the things that we learned about simple linear regression, and today we'll be expanding this to a multiple linear regression, and then we'll see how we can apply the same techniques in case of a multiple linear regression, both in R and as well as when we perform operations by hand. Okay, so the first thing is, what is actually multiple linear regression? Okay, so multiple linear regression is the same setup, but instead of one x, here we'll have multiple predictors. So here we'll have x1, x2, xp as p number of predictors. Okay, and here we are going to find out the effect of these on one response, that is my variable of interest y. Okay, so once we have that, we are going to see how we can apply these techniques for a multiple linear regression setting. Okay, so the first thing is, once we have this, then how do we get the OLS estimate? Because this is the first thing that we learned about the linear regression setup. So if you remember, if you remember how we obtained the OLS regression, so we had a scatter plot, we plotted x versus y, okay, and we had something like this, and we would actually draw a line, okay, and then we would gauge the vertical distances of these points from these lines, and then we'll try to minimize sum of squares due to errors, okay. So we are going to apply the same technique, and here we are going to see how to get the sum of squares due to errors. So initially, when we had one equation, I mean one predictor variable, at that point uh, it was the model was like this: y equal to alpha plus beta x plus epsilon, okay, and we were doing y minus alpha minus beta x, this is the epsilon whole square summation, and we were trying to minimize this quantity, okay. Here the regression the setup is something like this. So here the regression line is this is y equal to x beta plus epsilon, where beta is a p cross 1 vector, y is y is an n cross 1 vector, okay. This is n cross p and this is also n cross 1. All right, this is the model. So therefore sum of squares due to errors, okay, would be in a matrix setup, it can be written as epsilon transpose epsilon, okay. That would essentially mean summation epsilon I square I equal to 1 to n, okay. This is the sum of squares due to errors. So if we just expand this thing in terms of epsilon, we can write it as y minus x beta transpose y minus x beta, okay. So this is the quantity that we are trying to minimize. So we can rewrite it as y transpose y plus beta transpose x beta minus 2 beta transpose x, okay. So this is the quantity that we can write as beta. This is the quantity that we are trying to reduce, okay. So how did we do it in case of a simple linear regression? In case of a simple linear regression, we differentiated with respect to the beta parameter, okay. So here again we'll do the same thing. We are going to differentiate with respect to beta and then see how it goes. All right, so what we do here is this thing. So we come here, we do del s beta by del beta and then equate it to 0. So here the beta containing terms are these and these, okay. So when we do that, if we do del s beta by del beta, then it becomes something like this, okay. So if you remember, here we have something like this. Let's say we have alpha prime x alpha and d alpha, okay. So this actually amounts to 2 into x into alpha, okay. And similarly, if we have a quantity like this, then del alpha of alpha prime x is actually x. Okay, so here the term was y prime y minus, plus beta transpose x beta minus 2 beta transpose x transpose y. Okay, so this one is actually 2x alpha. So here x is x transpose x, so we'll write 2x transpose x beta minus, this is with respect to beta, so only the other terms will have, so 2x transpose 2x transpose y. Okay, and then we'll equate this to 0, and then if we rearrange, then what do we have, which implies 2 will cancel, beta x transpose x beta equal to x transpose y. So beta hat is actually x transpose x inverse x transpose y. So this is how we are going to get beta hat OLS, that is x transpose x inverse x transpose y. Okay, so this is the ordinary least square estimate of beta 1. Okay, now if this is beta hat OLS, what is y hat? That is the fitted model. This is x beta hat. Okay, so this one is x into x transpose x inverse x transpose y, and this quantity we can write as hy, and h is called, this is actually called the hat matrix. Okay, and this hat matrix has a few properties, that H is symmetric. Okay, so H equal to x transpose, that is equal to x into x transpose x inverse x transpose, this is H, and if we do H transpose, that is also equal to H, so that is symmetric. Okay, and so it has three properties. Property number 1 is H is symmetric. Property is H is idempotent, which means H squared is H. Okay, and third property is that trace of H is equal to P, that is number of predictors plus intercept. Okay, and this X matrix that I was talking about here, x beta plus epsilon, so if this is the model, I can write it expanded like this, y1 y2 yn for n number of individuals. This one I can write as a matrix. So the first column is, let's say, 1 1 1 1 1, and then we have x1 values, then we have x2 values, and then we have xp minus 1 values. Okay, but with the intercept term, it's an n cross p matrix. So this one would be beta naught, the intercept, then beta 1 to beta p minus 1, the other regression coefficients, plus epsilon. Okay, now once we have the hat matrix, once we have H, we can find the residuals by y minus y hat. So this is actually y minus hy. So this would be I minus hy, and since h is idempotent, I minus h is can be written, no sorry, this is I minus h into y. Okay, and I minus h also has the same properties. So I minus h is also symmetric. I minus h is idempotent, and trace of I minus h is equal to n minus p. Mind you, this p is including the intercept term. Okay, so once we have this, we are going to see how we can use the R software to get the equation and the fitted models. Okay, so we learned how to use the multiple linear regression software, the R software, for our calculations. Right, so let us first, I hope the screen is visible. So let us first find out our data set, which was empty cars. All right, so we have data on certain number of 32 cars, I think. Let's just check once. So n row of empty cars was 32. Okay, and we had these variables we were trying to predict. In the simple linear case, we were trying to predict the effect of weight on mpg, miles per gallon, and in this section we are going to learn about how we can incorporate the other parameters in the model. Okay, and it is very very simple. It is similar to what we did. Okay, so if we want to regress mpg, miles per gallon, on, let's say, 4 variables. Let me just do it. Let those be SIL, DISP, HP, and weight. Okay, so let these be my variables of interest, and we want to regress MPG on these 4 variables. So the command remains the same, that is lm. We are going to do it with lm. So lm y is MPG in this case, regressed on all of these. We are going to add with a, instead of comma, we are going to add a plus sign over here. Okay, and then we are going to give data. We are going to give here data equal to empty cars. So once we run this, we see that these are the coefficients. Okay, this is the intercept, and these are the regression coefficients that we would have wanted. Now if we did not want the intercept term, okay, so this one by default is with intercept. But had we not wanted intercept, so in case of no intercept, we would be writing the same thing, but instead of starting with CIL, I am going to put a -1 plus. Okay, and then we'll see. Okay, LM. And then we'll run the regression model, and now we see that we do not have the intercept term. All right, so once we have these values, let me just rename these to model no intercept and the first one, let that be model. Okay, so model is this one, model of no intercept is this one. All right, now how do we get the coefficients? Okay, so these are the coefficients that we've already got. How do we get the residuals? So to get the residuals, we are going to write resid, and then we are going to put model. So now if we do that, we see the residuals for each of the models, the response minus the fitted values. How do I find the fitted values? So fitted values, I am going to give fitted dot values, and then I'm going to write model, and here we get the fitted models, fitted values. Okay, if we do a summary of the model, we are going to find the estimates, standard errors, the t values, and the p values. These are essentially, I am going to rediscuss this when we touch up the testing of hypothesis part. Okay, and we can also do an analysis of variance. So this one actually partitions the total sum of squares into 4 distinct groups. Okay, I mean it is going to partition the total sum of squares into sum of squares due to the regression, and then one would be sum of squares due to the residuals. Okay, nice. So this is how we are going to use the regression lm command in R, and it will give us the results in no time. Okay, now once we have that, we are going to learn a little bit more about model fitting. Okay, so instead of doing this, if we would have had some data that what I mean to say is that if the situation was such that we would, instead of getting a ready-made data frame like this, we would have had to enter values manually, and in that case we would just need to populate like this. So x1 we are going to put, and then within C we are going to put the values and make it. So this would be value 1 comma value 2 comma and so on. Okay, similarly if I write value 1 1 value 1 2 similarly, and x2 would be the same thing, and then after entering everything we would have to use the lm command to run the multiple linear regression. Okay, so once this is done, let's move on to see how we can look for correlation plots using the R software. So we are going to learn about correlation plots. What does correlation plots give you? So correlation plots are supposed to be like scatter plots. Here, since we have multiple variables, it is difficult to plot all of these together and get some estimate out of this. Some estimate of the degree of correlation that we are having. So in such scenarios, correlation plots help a lot in assessing the pairwise correlation between any two of the variables. Alright, so here we have, how do I get to the correlation plot? So we are going to use one of the well-known functions, which is called pairs. Okay, so if we write it like this, pairs, and then we write the equation something like this. So we are going to write y, that is mpg, plus all my variables, mpg plus this thing, and then I am going to, this would be a matrix scatter plot. Alright, so here we are going to use this to get our matrix scatter plot. So see, this one helps me generate the matrix scatter plot where I have, so this one would be scatter plot between cycle CYL and displacement. This one would be the scatter plot between MPG and CYL. Okay, and these are like scatter plots with itself, so it doesn't really make much sense to plot a variable against itself. It will always be a straight line. Okay, so this is how we can write a not a correlation plot, this is actually a matrix scatter plot. Okay, right, once we have this, let's find out how we can use a correlation matrix. Okay, so in order to use the correlation matrix, we would have to manipulate the variables a little bit. So here, what did we have here? In the model thing, we can obtain the X matrix. So X matrix is obtained by model dot matrix model. Let me see what it gives. Okay, so this is actually the x-axis variable. Now if we want a correlation plot, what we have to do is that we have to do let me put x1, I'm going to put C bind, and I'm going to bind the y values, that is empty cars $mpg. Okay, that comma x, so I just want all rows and or I just want all rows and 1 2 3 4 5. So instead of getting this one, I'm going to give the model no intercept, that way it will become easier. So this is x, okay, with all the variables, and we are going to just do a simple C bind so that the y variable is also found. So x1 now has y and these things. Okay, so if I just write call names x1, the first one is blank, so I'm going to assign it to mpg. Alright, and then let's see how x1 looks. So now x1 looks like this. And now what do we have to do? We'll just need to install the package corplot. So we are going to do that, install dot packages corplot. Then we are going to load that package into memory, and then finally I am going to do the correlation matrix. So if I just write cor or cor, and then I put x1, so see, I get the correlation matrix like this. Okay, and if I want to so I'll save it as core x1 equal to this thing, and then if I want to plot it, all I need to do is I have to write a chord plot, provide the correlation matrix, and let me write method equal to number for the time being. So here we have reported what is the correlation between each of these variables. So if we have a negative correlation, we are going to get these red marks, and then if we have a positive correlation, we are going to get these blue marks, and the intensity, how dark or light it is, will depend on the numerical value. Okay, so instead of getting the numbers, if we want it something like a heat map, we can also, instead of using number, we can use shade. So let's see what this gives me. So shade gives me something like this. Okay, and if we put method equal to ellipse, then we are going to get something like this. Okay, so this is how the scatter plots would have, so the shades of font colors and width of ellipse in the graphs. And if we want the visualization, what is here, they've given us full explanation. Okay, so areas of squares or circles show absolute value of the correlation. Okay, so this is how you would obtain and fit an OLSE using the R software. Okay, okay, and once we have these, we can definitely go ahead, and we learned how to get the fitted model, how to get the summary, and how to get the residuals, and then go about it. Alright, so now that we have learned how to tackle this problem using R, let us go back and look at some of the theoretical aspects of this multiple linear least square technique. Okay, so we have learned all of these. So the next thing that we also looked at in the case of a simple linear regression was the properties of the estimator. So we are going to do that here as well. So we are, okay, where did this go? Okay, so we were talking about the properties of OLS or estimators. So in case of a simple linear regression, we learned that OLS is unbiased. So is it, so let me just write it here. I'm going to write these are the properties. Okay, so first is it unbiased? Answer is yes. So that means expectation of beta hat is equal to beta, or expectation of x transpose x inverse x transpose y is equal to beta. Alright, so once we have this, so the next thing that we would want is the covariance matrix of beta hat. Okay, so this is given by, so variance covariance matrix of beta hat. So variance covariance matrix of beta hat is expectation of beta hat minus beta hat minus beta transpose. So this comes to sigma square x transpose x inverse. Okay, and sigma square is estimated by 1 by n minus k y minus x beta hat y minus x beta hat. Okay, so this is given by s square, and thus the variance covariance matrix is estimated like this. So this is sigma square hat x transpose x inverse. Okay, and the covariance matrix of y hat, so variance of y hat is actually given by sigma square into h, and since sigma square is unknown, variance of y hat is given by sigma square hat into h. Alright, and this OLS estimator also has certain other nice properties. So the first one is that it follows following the Gauss-Markov theorem. So what were the assumptions of Gauss-Markov? The assumptions were expectation of epsilon is 0 and variance of epsilon is sigma square I, and x's are non-stochastic. Okay, just give me excuse me for a bit. Okay, so the under the Gauss-Markov model, what we have is that the OLS estimator is actually blue. that is best linear unbiased estimator. And by this we mean that by best linear unbiased estimator we mean that it among the category of unbiased estimators, this estimator has minimum variance. Okay. So apart from all these properties, we also have some other properties which are this. So the next thing is consistency. Okay, so this is OLS estimator. So if I see beta hat OLS is consistent. Okay, and for beta and sigma square hat is consistent for sigma square. So what does it mean to be consistent? So consistency means that if I increase my sample size, then the probability that this estimated value is arbitrarily close to the true value So consistency means that this estimator converges in probability to the true beta values. Okay, so in probability convergence is guaranteed by this consistency clause. Consistency, not clause, property. Right. So next what we are going to learn is this thing. And then we also learn that the Kramer-Rao lower bound of beta and sigma square is this thing, sigma square x transpose x inverse 0 0 2 sigma to the power 4 by n. And sigma LSE is given by sigma square x transpose x inverse 0 0 2 sigma to the power 4 by n minus k. And this says that Kramer-Rao lower bound is attained for beta but not sigma square. Okay, so the next thing that we need to take care is actually testing of hypothesis. Okay, so the next thing that we are going to learn is actually testing of hypothesis. Okay, now if I want to test for individual hypothesis beta equal to 0 versus beta not equal to 0, that is testing the individual regression coefficients. Okay, so if h is if h naught is not true, that is h naught is rejected, that means that the variable x, the corresponding variable x has a significant effect on the response y. Alright, so the test statistic for testing this one is actually t, which is given by beta. So here I am going to test beta j, so this would be beta j hat by standard error of beta j hat, and this would follow a t n minus p under h naught. Mind you, this p is including intercept. Okay, this p, so this follows t n minus p. This p is actually number of columns in model dot matrix. Okay, given that all columns are independent. Okay, if all columns are not independent, then we wouldn't have a unique estimate of beta, because then x transpose x would not be invertible if it had less rank than the number of columns. Okay, so the standard error, so this is actually the test statistic, and the standard error of beta j hat is given by sigma square into cjj, where cjj is the jth diagonal element of x transpose x inverse. Okay, and the rejection rule is we'll reject h naught if and only if p-value less than alpha or mod t is greater than t alpha by 2 n minus p. Okay, now we can carry out this test itself in R. And how do we do that? We need to use the element, we need to use the summary column. So if we come here, this summary model is going to give us this and this. Okay, so if we divide this by this, we are going to get the t value, and then this actually is what the p value ranges are, and then from here we will be able to calculate the observed value of the test statistic as well as what is the critical value. Okay, and if this p is less than alpha, then we say that okay, this is an important variable in explaining the variation in my response variable. So from here I can see that weight is an important one because it has a less p value, and the intercept is also a very important variable, and we cannot do away with this. But here this TISP, HP and CYL, they do not have a p value less than 0.05, so we don't say that they are as important. Alright, now this was actually testing for single coefficients, but if I want to get the confidence interval, and how do I get that? So here we need to make the assumption. So for testing of hypothesis, till deriving the OLS estimator, we did not need any assumption. But once we come to testing of hypothesis, we will need an assumption, and we usually assume that y follows normal distribution, or in other words, I would say that the errors follow normal distribution. Okay, we'll have this similar assumption when it comes to getting the confidence intervals as well. Okay, so we'll assume that epsilons are IID following normal 0 sigma square. Okay, and y follows normal x beta plus, so y is x beta sigma square I. Beta hat is following normal beta sigma square x prime x inverse. Okay, marginally, if I have a beta j hat, then this also follows normal beta j, and then sigma square cjj, where cjj is described. Okay, and tj is given by beta j hat minus bj by root over sigma square hat cjj, and sigma square hat is given by sum of squares due to residuals by n minus p. Okay, and that is y transpose y minus beta hat transpose x transpose y. Okay, so from here we can derive, so 100 into 1 minus alpha percent ci would be given by this. So if t is a symmetric distribution, this is t alpha by 2 such that the area above this curve area is alpha by 2. Since it's symmetric about 0, this one would be minus t alpha by 2. That area below this would also be alpha by 2. So if I want to devise a confidence interval, all I need to do is this one. So probability this one minus t alpha by 2 n minus p less than equal to beta j hat minus beta j by root over sigma square hat cjj less than equal to t alpha by 2 n minus p. So this probability of this unshaded region is actually 1 minus alpha, right? So if we just reshuffle this a little bit, we all need to do is we need to keep probability bj and then get reshuffle and get the other terms of the confidence interval. We will see that it would come out to be beta j hat minus t alpha by 2 n minus p root over sigma square cjj and beta j hat plus t alpha by 2 n minus p square root of sigma square cjj. Okay, and how do we get this in R? So in R we just have to write conf int model. Okay, and then just we'll have to specify the level. So if I want a 90% confident interval, I would say 0.9, and see here I get all the individual 90% confidence interval. if I want it for 95%, this is the thing. So don't get confused seeing 5 and 95 and thinking that okay, this is 95. No, 5 and 95 total, I mean below 5% and above 90% actually accounts for 10%. Okay, and similarly below 2.5% and greater than 97.5% will together account for 5%, and that is how we should be taking this. Okay, so for intercept, this is the um, confidence interval. For all these variables, these are the confidence intervals. Now if confidence intervals carry the term 0, then actually the hypothesis is accepted, that null hypothesis, otherwise it is rejected. So that's also another way to check. Alright, so this was all from my end. Hope these will help you solve the assignment questions. Thank you so much for joining.